Okay, so our next speaker is On-Hei Low from Tongji University, talking about cycles in polyhedral graphs.
Thank you for the introduction. And yes, I'm from Tongji, which is in Shanghai. And very happy for my first time in Australia in the WSU seminar. So yeah, my talk is will be very simple, and I just want to give a very brief introduction of what I'm interested. Cycles in polyhedral graphs. So Carol said that I should start with the definition of graphs. So it is simple. We have an order pair, V and E, and V means the vertices, E means the edges. So here we have a representation. The dots are the vertices and the lines are the edges. So you can say that edges is just a binary relation of the vertices. And we just consider the simple graphs. So we do not have this kind of configuration. So very, and it's also finite. So let's have some more definition about the graph property. The first one is planar, which means in the two-dimensional plane, you can embed your graph on it such that everything is injective, so no two edges can cross each other. So here is an example, and actually all properties, we will take this example. And we say that, for example, two vertices and one edge, we said that this edge is incident to its n vertices. And the degree of a vertex is just the number of edges incident to that vertex. In this example, in this vertex, it has degree 3. It has 3 neighbors. Okay. And if every vertex has the same degree d, we said that this graph is d-regular. So this graph is a 3-regular graph. And we said that a graph is bipartite if you can partition the vertices into 2 parts, and every edge has exactly 1 vertex from each set. Here we represent the 2 sets by coloring the vertex with a white or black. So every edge you have 1 black vertex and 1 white end vertex. So here is an example, which is 3 regular, bipartite, and planar. So that's so good. Then we also need some more definition, which is we call it a subgraph of a given graph. So the first kind is we call it a path. A path, here is the rigorous definition, but I think it's very easy to understand with this figure. We have some distinct vertices, and we just go from one to another one consecutively via some edges. And a cycle is similar, but we will go back to the starting point. So it's path and cycle. And other fundamental notion is the connectivity. A graph is connected if every pair of vertices can be joined by some path. So this graph is connected because you can pick any 2 vertex, you can find a path which connects them. And we can measure how well it's connected. We use the k-connected, which means that if you delete less than k vertices, the graph still connected. If you delete any k-1 vertices, if it is still connected, then we say that it is k-connected. So this graph is 2 connected because you can delete any vertex and also the incident edges, and the graph stay connected. But this is not too connected because you can delete 2 minus 1 vertexes, which means you can delete 1 vertex, then it will fall apart. And this graph is 3 connected. So yeah, this is only 2 connected, but not 3 connected. But this is 3 connected. So one simple fact is that if your graph is k connected, then every vertex has degree at least k. Otherwise, you just take that vertex and you delete its neighbors. If its degree is less than k, which means you delete less than k vertices, and it will be disconnected. Yeah. Okay, so we will introduce what is a polyhedral graph. So it is in our title. So it is what we are interested. So a polyhedral graph is from any polyhedron in the 3-dimensional. So you take any polyhedron you like, then you just consider one skeleton. So we know that the 0-dimensional one is the vertices, and the 1-dimensional ones are the edges. So it will naturally correspond to a graph, right? We have vertices and we have edges, so it is graphs. So we call these graphs polyhedral graphs. So you see that we have this graph is sort of having a 3-dimensional representation, but it is very easy to make it in the on the plane. So how to do this? One way is to you pick any face of your polyhedron, then you take a point which is a bit away from the polyhedron. Then everything can be just mapped on this face. So the polyhedron we have here, and I take this face and take a point near enough, close enough to this face, and I project everything just on this face, we get this graph. So obviously, this graph must be planar, and actually it is also 3 connected. It is also 3 connected, which means delete any less than 3 vertices, it is still connected. Yeah, we can try, but for example, I delete this and this, the remaining part is still connected. I can try delete this and this, it is still connected. So we can ask why it is still 3 connected, and actually it's not very hard to show this. We already know that we can embed it on the plane. If it is not 3 connected, say if we have a 2 vertex cut, I mean if deletes 2 vertices, it will fall apart, which means that we can find a simple closed curve which intersects this graph with only 2 vertices. Because we delete that 2 vertices and the remaining parts will be separated, so we have a simple closed curve on the plane just intersect with those 2 vertices. And that will be a problem. Why? Because we have 2 vertices and one simple closed curve. Then those 2 vertices divided the simple closed curve into 2 parts, right? 2 parts, and each of these parts are in some phases. But with this projection, each phases is convex. It's some convex polygon. So which means that the 2 phases must be having exactly one common edge. I'm not sure whether my explanation is clear enough, but if so, then we know that those two vertices we delete are actually from one edge. So yeah, it must be, for example, if you want a simple closed curve which intersects this graph with only two vertices, those two vertices must be adjacent, and your curve is actually like this. So it is not separating anything. It's not separating anything. And interestingly, the converse of these statements is also true. It is a very fundamental theorem of the polyhedron. Stein's theorem, which says that a graph is a one skeleton of a convex polyhedron, which means a graph is polyhedral if and only if it is planar and three connected. So which means that if we want to study polyhedral graph, we just need to focus on planar and three connected graphs. And from now on, we will call this graph just a polyhedral graphs. Okay, so that is one of the objects mentioned in the title. And another object is cycles. So we are going to see about cycles in polyhedral graphs. So one of the classical cycles are called the Hamilton cycles. So a Hamilton cycles of a graph is a cycle that visits every vertex of a graph exactly once. Here we have the graph of the dodecahedron. Is the dodecahedron embedded on the plane? And the red edges forms a Hamilton cycle. Yeah. You can see that it visits every vertex exactly once, so it's Hamilton cycle. So it is introduced by Sir William Rowan Hamilton, who invented a game called Icosian game in 1857. And in most texts, we will say that the objective of the game is to find a Hamilton cycle on the dodecahedron. But actually, it is a bit simplified because actually the game is a bit more complicated. For example, the player, it is actually played by two people. The game is played by two people, and there are different questions. For example, one of the questions, the first player is asked to first go for five step. I mean, for 5 vertices, for example, the first player can choose 1, 2, 3, 4, 5. Then the second player are asked to finish the Hamilton cycle. Yeah, so this notion of Hamiltonicity is popularized by Hamilton's Icosian game. And actually, Hamilton invents this game because he wants to invent some algebraic system using the symmetry of dodecahedron, the symmetry of icosahedron, so it's called Icosian game. Yeah, but the algebraic system itself is not as successful as another work of Hamilton, the quaternion, but interestingly, it leads to this Hamiltonicity. Another interesting story is 1 year before Hamilton introduced the Icosian game, another mathematician, Thomas Kirkman, he also studied similar notion. He also studied Hamilton cycle. But what he wanted to do is he wanted to study the representation of polyhedron. So he somehow discussed that if I have a polyhedron and its dual, if we know a Hamilton cycle of each of them, we can use them to represent the polyhedron. But actually in Kurtzman's paper, there are some false claims. Anyway, in his paper, he introduced, he gives probably the first example in the literature that a polyhedral graph that has no Hamilton cycle. And this is the Kurtzman graph, which has 13 vertices. Yeah. And it has no Hamilton cycle. So what we will call is if a graph that has a Hamilton cycle, we call it Hamiltonian. And if it has no Hamilton cycle, we call it Kurtzmanian. So another interesting fact is that Hamilton and Kurtzman met in 1861. Yeah, so Kurtzman's paper appeared in 56, and the Icosian game is 57, and they met in 61. Actually, Hamilton visited Kurtzman. At that time, Kurtzman is a rector of some high school. I'm not sure the terms, but yeah. Okay. So the Hamilton cycles of polyhedral graphs is actually very interesting. One reason is that it is related to a proof by Tait for the four-color conjecture. At that time, it's still a conjecture, but actually at that time there is another proof, another false proof of four-color conjecture by Kemper. So at that time, actually Tait believed the four-color conjecture is solved, but he still want to study it to find an alternative proof. So he did figure out a proof, but that proof is based on a hypothesis that every three regular polyhedral graph has a Hamilton cycle. Yeah. And also a story about this thing is Tait actually consulted Kurtzman about this hypothesis. And Kurtzman said that the proof is most alike as doubt and proof. So interesting to know it. Okay. So Tait's proofs appear in 1880. So like 66 years later, William Tutte gives a counterexample to Tait's hypothesis, which means that Tait constructs an example which is a three-regular Kurtzmanian polyhedral graph. So this graph is polyhedral. You can try that it is planar and three connected, so it is polyhedral. And it is also three-regular. Every vertex has exactly three neighbors, and the total number of vertices is 46. And later, there are also smaller counterexamples. Actually, the smallest counterexample has 38 vertices. And there are 6 such graphs. One of them is drawn here. So you can see that this part is actually this part. So it's a very interesting gadget. Actually, if you have a Hamilton cycles, you can focus on this, and you know that, okay, I must enter is and somehow visit all vertices here and go out. you can go out by here or here, right? So the property of this is if you want to go inside and visit all vertices, it is not possible to enter here and exit here. So if you want to visit all vertices, you must use this exit or entry, which means that if you want to visit all vertices, you must go to this vertex 3 times. So it is not a Hamilton cycle. So it is the strategy of this construction. Okay, so we have seen some interesting Riemannian polyhedral graph, and they are 3 regular. So but we can ask whether we can have a smaller Riemannian polyhedral graph if we do not require that it is 3 regular. We have seen one. We have seen one very small, which is the Kirkman graph, which is much smaller than the Tait graph. So, but still we can ask what would be, is it the smallest or there is a even smaller? And yes, we have the smallest one is the Herschel graph, which has no Hamilton cycle and which has only 11 vertices. The Kirkman graph has 13 vertices, but it has only 11 vertices. And actually, the Herschel graph is the smallest Riemannian polyhedral graphs in terms of both the number of vertices and the number of edges. So which means we cannot find any smaller Riemannian polyhedral graph. So the Herschel graph first has already appeared in Coxeter's book, which is 1948. But Coxeter did not prove that it's the smallest one, and it is proved by Barnett and Jukovic, I think in the 70s. And later, Dulancott also writes a paper which is about using computer to check many polyhedral, and he also confirmed it by a computer. And yeah, there is a interesting question. So how did Kirkman prove that the Kirkman graph has no Hamilton cycle? Does anyone want to try? It's actually not difficult. Okay, the answer is this. Because no matter the Herschel graph or the Kirkman graph, they are bipartite. And they have, if they are bipartite, every cycle of this graph must have an even length, right? You go from black to white to black to white, and finally go back to black. So it must be even length every cycle. But the number of vertices is odd. So it has 13 vertices, 11 vertices. So it's done. Yeah. So you cannot have any Hamilton cycle. And yeah, that's the way Kirkman proved that this is has no Hamilton cycle. So before continuing, I will introduce another important notion of graphs, which is graph minus. If we have a graph G and we delete some vertices, edges, or contrast some edges, we can obtain a minor of G. Let's say the smaller one is H. Here, contrasting edges means you have an edge and you identify these n vertices to So it's contracting edges. So for example, if you have a planar graph, it is embedded on the plane. Of course, if you delete something, it is still on the plane. And you can also contract edges, and it is still embedded on the plane, because you can imagine it's something like a homeomorphism of your graph. So graph minus is very important in graph theory. Another observation is if you have a graph and you have a minor of the graph G, then the smaller graph cannot have more vertices or edges than the original graph. One very important theorem in the graph minor theory is the Robertson-Seymour theorem. We said that the minor relation is actually a well-Poisson ordering on any graph class. So if you have a class of graphs and you order them by minor, and first of all, it is a partial ordering. It's not hard to see that. And actually, that partial ordering is well-Poisson order, which means that if you have an infinite sequence of graphs, then you can find two graphs such that the earlier one is a minor of a later one. And I think in the 1930s, Kuratowski and Wagner proved a very important theorem. They characterize the planarity by graph minors. The theorem said that a graph is planar if only if it does not contain K5 minor and does not contain K33 minor. So what does it mean? It means that, okay, this graph is K5, this graph is K33. If we have a graph which is planar, then it is if only if it has no K5 as a minor and no K33 as a minor. And it is an example. For example, if we have this graph, we want to show that it is not possible to embed it on the plane without crossing edges. What we can do is we show that this graph has a K5 minor. So why it has a K5 minor? Because we can contract these 5 edges, then it will become a K5. Therefore, this graph is not possible to be embedded in the plane. Okay, so I'm very interested in the minors of Kirkmanian polyhedral graphs. So what we now consider is we consider the graph class consisting of Kirkmanian polyhedral graphs. And we order these graphs by minor relation. So we say that a graph is larger than another graph if the smaller one is a minor of the larger one, right? Which means that you can obtain the smaller one by deleting some edges, vertices, and contracting some edges to obtain the smaller one. So we use minor relation to order this whole class. Okay, so by Robertson-Seymour theorem, we know that there are some minimal elements of this ordering. Moreover, there are only finitely many elements in the which are minimal. So we want to find out what this finite family is. So recently, with Kenta Ozeki, our next speaker, we proved that this finite family consists of only one graph, which is the dodecahedral graph, which means that we prove every Kirkmanian polyhedral graph must contain the Herschel graph as a minor. So if you give me any Kirkmanian polyhedral graph, I can, from this graph, I delete something and I contrast some edges, I can obtain the Herschel graph. Let's see an example. We have a Kirkman graph here. We delete this green edge and we contract these two red edges. So we get this. And this graph is actually the Herschel graph. You can try to correspond to color labels. You can see that the green is to 3 blue, green to 3 blue, and then 2 blue to 1 red, 1 red, 1 red, and also another 2 blue to 1 red, 1 red, 1 red. It's exactly the Herschel graph. Green to 3 blues, and every pair of blue vertices on one side will go to 1 red. So we just see that the Kirkman graph, according to our theorem, actually is containing the Herschel graph as a minor. So our results actually unify a couple of results. One of them is we just mentioned that the Herschel graph is the smallest Kirkman polyhedral graphs in terms of both number of vertices and the number of edges. So actually, this can be the corollary of our result, because in every graph in this class, you have Herschel graph as a minor. So this graph must have the number of vertices and edges must be at least as those of the Herschel graph. So this result generalize the fact we stated for the Herschel graph. Okay, so I will talk about a few related questions, 2 open problems about Kirkmanian polyhedra. And actually, I think it's very closely related to the Tait graph. The Tait graph we saw before. I mean the counterexample to the Tait hypothesis. So it's a 3 regular Kirkmanian polyhedral graph. So we can also ask whether there is 4 regular Kirkmanian polyhedral graph. And the answer is yes. And it is a very interesting graph found by Van Hilgut and Zabilescu, so it's by Carroll. It has 39 vertices. And they conjecture that it is the unique, the smallest 4 regular Kirkmanian polyhedral graph. And for your information, they also show that there is no 4 regular Kirkmanian polyhedral graph with fewer than 35 vertices. So they emphasize that they conjecture that this graph is the unique, smallest one. So I'm not so sure what approach we can try. Maybe by better computer. I don't know. Yeah, but maybe this bound is by computer. Okay. Yeah. Yeah, but this graph is found by hand. Yeah. So it would be really great if this conjecture holds. Another conjecture, Tait show that if it is 3 regular polyhedral graph, it has there are some of this graph have no Hamilton cycle. So in 1969, Barnett conjectured that if we add the bipartiteness, then this graph must have a Hamilton cycle. So I think this conjecture is very, very big, very big, and many researchers try it, but we still don't know. We still don't know whether it's true. And yeah, a few days ago, we Raymond also discussed about this conjecture. Okay, I also want to introduce some other results. One of the results is okay, we know that a polyhedral graph may have no Hamilton cycle, but actually even they have no Hamilton cycle, they must have some sort of long cycle. Chen and Yu, they proved in 2002 that if your graph has n vertices, then you must find a cycle. Its length is at least n to the power log 2 with base 3. So it's roughly 0.6, n to the 0.6. And this exponent is best possible because of this kind of construction, which is just you start with a triangle, then you subdivide the triangle, you get 3 interior triangle, and you keep subdivide them, then you get this construction showing that it's best possible. And we just see some long cycles. The Hamilton cycles are very long, the longest one. And actually, we also have some results about short cycles. Actually, it is you should see it in every graph theory course that if you have a polyhedral graph, then actually it must have a phase. The length of it is 3, 4, or 5. Here is a very short proof, but I will just skip it. So we sort of generalize this notion in the following way. If we have a polyhedral graph, such that it has some cycle of length at least k, then we want to know can we conclude that it must have a cycle of length between k and some fixed integer f of k, which only depends on k. So what we have just seen is that we must have a cycle between 3, 4, or 5. So which means that if you choose k to be 3, we know that the polyhedral graph must have a cycle of length between 3 and 5. So that shows that it is f3 is at most 5. And actually f3 is equal 5 because we have the dodecahedron, which has no cycle length 3 or 4, but it has cycle length 5. So it is tight. So you can understand it's okay. We want to find some interval for every given k. For example, k is 3, then 3 to 5 is an interval to ensure you that you must have some cycle of this length in your polyhedral graph, given that your polyhedral graph has some cycle of length at least k. Yeah, if it has no, then of course this interval will become void. Yeah. So together with my colleague Tait, we actually determine all the exact values of fk. So for all k at least 5, we prove that fk is 2k plus 3, which means that if we have a polyhedral graph, and that graph has some cycle of length at least k, then actually the cycle, you can find some cycle length not far away from k, because between k and 2k plus 3, there is some cycle length. So okay, finally, let's introduce another classic result about cycles of polyhedral graphs. It is by Tutte, who has a counterexample to Tait's hypothesis, which is a negative result. And he also has a positive result. If we raise the connectivity from 3 connected to 4 connected, then your polyhedral graph must have a Hamilton cycle. And there are some conjectures want to improve Tait's result. But both of them are still largely open. Let's take, for example, the second. The second said that if your 4-connected polyhedral graph has a 4 cycle, then it must have all possible cycle lengths from 3 to n, and if n is the number of vertices. So you can see that not only having the longer cycle, it's actually having almost all cycle lengths. You can find them all. And we know only a very little about the existence of certain cycle lengths. And here is an example of why we need to be careful about the cycle length 4, because there are some 4-connected polyhedral graph which has no 4 cycles. Here is the example. Okay, so it's all of my talk. Thank you.
Thanks. Any questions?
Bergmanian, this is your idea, right?
Yes. Yes. This terminology first appear in this world. Yeah. Yes. Yes. So every polyhedral graph is either Hamiltonian or Kalman.
Something that I missed. You were talking about phase cycles at some point. Could you help me with that?
Phase
Cycle.
this.
Yes, every polyhedral graph contains a phase cycle of like 3, 4, or 5. What is a phase?
It's just correspond to a phase.
Oh, okay. So,
if you have a phase, the boundary is a cycle.
Okay. Yes.
And it's spatial cycle.
Oh, okay. Okay.
Okay, if there are no more questions, thanks a lot again.